So I suggest to start. So good afternoon and welcome everybody to the HiDALGO workshop at the HiPEAC event. This is a virtual workshop today, and the whole HiPEAC event is virtual due to the COVID crisis. And in this workshop, we are dealing with, so the title of the workshop is Tackling Global Challenges by Use of HPC, HPDA and AI. Within this workshop, we will have basically 5 talks and a roundtable at the end. The workshop is divided into 3 sessions, and in each session we will have something like 2 talks. So 2 talks in the first and second session, and in the third session a talk and the roundtable discussion. I'm chairing the first session, and I'm very happy to introduce to you 2 speakers who are both heavily involved in the HiDALGO project. And the first speaker is Sergiy Gogolenko from the HLRS, High Performance Computing Center in Stuttgart. And he will talk about the project HiDALGO, an introduction, its services and its portal. So Sergiy, thank you very much for agreeing to give this talk, and we look forward to your presentation.
Thank you, Robert. So let me share the screen. Okay, so let's start. Hello, everyone. Welcome to the workshop on tackling global challenges with high-performance computing and high-performance data analytics technologies. Since half of the talks today will be related to the work done in the frame of European Cluster of Excellence for Global Challenges called HiDALGO, we decided to start our workshop with the high-level presentation of this project. In this opening talk, I will briefly introduce you to the HiDALGO objectives, use cases, and its services. Global challenges gain a solid attention from the society. They are broadly discussed in the media. Almost daily we hear news about wars, pandemics, climate change, and other troubles from the TV, newspapers, Twitter, Facebook, and so on. We won't have Netflix documentaries about global challenges. The Netflix, which main purpose by design is to entertain us. Moreover, we have new directions in conceptual art dedicated to global challenges, like, for example, climate change art. HiDALGO project was established in order to address the solid demand in the society to know more about global challenges and how to deal with them efficiently. We are an European Union funded project which brings together global system scientists as well as artificial intelligence and high performance computing experts from certain partner institutions out of 7 countries. The work is coordinated by ATOS Spain, and we are in the 3rd year of the project. Essentially, the goal of the project is to target computer-aided evidence-based policymaking for current and upcoming situations via accurate simulation of global challenges. The project focuses on 3 main objectives. First and foremost, we try to benefit from the synergies between high-performance computing, high-performance data analytics, artificial intelligence, and global challenges. In particular, we aim to establish a baseline for HPC, HPDA, and AI research in the domain of global challenges, focusing primarily on the highly accurate models. Our next objective is to provide a single entry point for decision makers and other relevant entities. To fulfill this goal, we developed a multi-domain portal for the global challenge communities. Last but not least, people working on global challenges usually come with different backgrounds. For example, in our consortium, we have global system scientists as well as AI and HPC experts. Our goal is to connect and train this diverse community. At the moment, there are many global challenges in the world. Now, the question is how to select the right one to study. Some thinkers tend to reason that famine, plagues, and wars are essentially problems of the former centuries, and humanity must look forward on the challenges of the future, like happiness, immortality, and godlike powers. In HiDALGO team, we have a more conservative view. Well, If we take a look on the news that dominate in the media over the last months, we still see pandemics and wars, besides other titles. So these topics constitute the use cases for our research. Our first use case deals with simulation of refugees and human migration. In this use case, we try to develop realistic models for simulating refugee streams, complete data collection of refugee movement, as well as to investigate the consequences of different policies like closing nation borders. This use case uses HPC in order to perform large simulation runs and ensemble runs. The HPDA is used to preprocess geospatial information, analyze weather and climate data, post-process simulation results, as well as synthesize inputs for the further simulations. Later on today, we will have a dedicated talk about pre-processing geospatial information for the purposes of this use case, given by Christoph Schweimer from No Center. The results of this use case were applied to study conflicts in Central African Republic, South Sudan, Mali, recent conflict in Ethiopia, and so on. We are also in touch with some NGOs like UN High Commissioner for Refugees and Save the Children. There is a lot of hype around infection spread simulation these days, and it's one of our use cases too. This use case, we try to simulate epidemic spreads across the local areas and to investigate the effects of applying certain policies. HPC is used again for establishing individual and assemble simulation runs. HPDA is used also to pre-process geospatial information for post-process simulation results, analyze weather and climate data, and synthesize inputs. We used this use case to study spread of COVID-19 in London and the cities of London and Madrid. Derek Groen from Brunel University will present synopsis of our results in these directions right after my talk. Our next use case is urban air pollution simulation use case. In this use case, we try to simulate pollutions in cities based on real-world sensory data. We also try to couple models for traffic, airflow, and weather simulation, as well as to design evidence-based decision models to leverage green growth. HPC is used as similarly to the previous use cases to run large individual and ensemble simulation runs. HPDA is used to impute the missing data from sensors, to perform model reduction tasks, and to post-process simulation results. We use this, our tools developed within this use case to study air pollutions in the cities of Győr, Graz, Milwaukee, Stuttgart, and some other. Last but not least, we have a social network analysis use case. In this use case, we analyze the structure of social networks and the stochastic behavior of the message spreading. We also simulate the spread of messages among users and study the spread of fake news in order to develop some countermeasures. In this use case, HPC is used to run some expensive network analytics, as well as to perform simulation runs. HPDA is used for feature extraction, retweet probabilities, modeling, and post-processing simulation results. HiDALGO approaches policy making via accurate digital twinning of global challenges. Accurate digital twinning for global challenges inevitably involve models for diverse social and physical phenomena, often multi-scale by design and consuming massive sets of static and streaming data. The generalized HiDALGO workflow is demonstrated on this slide. Such simulation-centric approach gives rise to a number of research topics related to coupling of models and data sources, as well as design of HPDA methods. One of such topics is coupling across data centers. In particular, our partners developed and implemented a toolbox called Polytope to enable acyclic asynchronous coupling across data centers. In our case, we use it to couple weather forecasts produced at the clusters of the European Center for Medium-Range Weather Forecasts with the migration and urban air pollution simulations done at the resources of the high-performance computing centers from HiDALGO consortium. In order to implement the simulation-centric approach, besides Polytope, we use, develop, and promote a bunch of other software tools. You can see some of them listed on this slide. In the domain of simulation, we use agent-based modeling and computational fluid dynamics frameworks, as well as specific linear algebra packages, some of which are developed by our researchers. In the domain of data analytics, we primarily rely on the well-established frameworks like Dask and Spark. For visualization, we use our developments Cobase and Visualizer, capable of tackling massive data sets and providing immersive visualization features. Finally, for orchestration purposes, for orchestration of complicated coupled simulation workflows, we use tools like Cloudify and FabSim. HiDALGO provides a bunch of services listed on this slide. In the next slides, I will quickly go through them. First of all, we provide consultancy services. We analyze problems, systems, codes, propose solutions, adapt modules, customize final offerings. We organize workshops like the one you are present today. Also, we prepare on-site trainings. Well, at least we did it before the COVID outbreak, and you can see photo from one of our on-site trainings on the background of this slide. Finally, we developed several online courses which are deployed on our Moodle platform. In addition, we support community by yellow pages, matchmaking tools, contributing to public discussion forums, and participating in different events. HiDALGO provides expert support through Zamat-based ticketing system and AskBot-based public forum, as well as a bunch of, we also provide a bunch of online documentation. Co-design plays a special role in our project. We work in both directions, software and hardware software co-design. As all we know, high-performance computing consumes a lot of electricity. One of our tasks is to make these consumptions as small as possible by selecting the proper hardware and tuning the software. Otherwise, while solving different global challenges, we will contribute to another one. While dealing with data-intensive tasks, we also establish data repositories and organize access to collections of massive real-world data sets, useful for tackling global challenges, as well as tools that facilitate access to this data. As I mentioned on one of the previous slides, establishing a single entry point for decision makers and people interested in global challenges is one of the fundamental objectives of our project. Therefore, we are keen on designing a convenient portal for our potential users. Currently, we have such portal components as marketplace, community tools, job submission frontend, data catalog, post-processing services, CI/CD infrastructure. You can get an impression about the high-level design of our portal from this slide. Last but not least, we are open for collaboration with individuals and organizations in all directions you see on this slide. All in all, if you have global challenges in mind, or you have interest in our research, our use cases, or our services, or you just want to leave your feedback, please feel free to contact us anytime. You can see contact information on this slide. Thank you for your attention, and I hope you'll enjoy the rest of the workshop.
Thank you very much, Sergiy. Are there any questions? I don't see questions in the chat, and I don't see anybody raising hands. So I assume there are no questions yet. However, you have always the possibility to post questions into the chat even after the talk ends. Now I have received a question. How does the project collect data for the complex simulations?
Okay, thank you for the questions, Vincent. So there are several ways in which we collect data. Well, we have Derek Groen in the call, and he can say more about migration use case. How do we collect data for migration and COVID use cases? But in general, the first way where we get data from is our data providers. We have three partner institutions. Let me go to the three partner institutions which are directly involved into providing data. These are Moonstar, who provides us telecommunication data, real-world data about calls between people in different countries. Then we have weather and climate data, which is provided by European ECMWF, European Center for Medium Range Climate Research. And we also have ARH, one Hungarian company which deployed sensors, different sensors, air quality sensors in the city of Győr, and also deployed a set of cameras in the cities of Győr, from which we can collect streaming data about air quality in this city and about the movement of the cars in this city. So these are our direct providers of data, and as well we also just do crawling of the data from the web. As for example, we crawl the data from Twitter using Twitter API for the purposes of the social network analytics use case. And I guess Robert can say a little bit more about the directions about the resources from which we get data for social network analytics.
Yeah, thank you very much. So concerning the social network analysis, there are also some freely available data. For example, the Stanford Network Analysis Platform, but we also did several historical power tracks from Twitter, for which we basically paid the data we obtained from them. So there are different sources we are using there. Further questions? I don't see any at the moment. Don't see further questions. So as mentioned before, there is always the possibility to pose questions to the talks even after the next talk has started. So thank you very much, Sergiy. And now we come to our second talk in this session. The second talk is given by Derek Groen from Brunel University of London, and he will talk about a very hot topic at the moment, which is the COVID-19 epidemic, and he will talk about simulating the spread of COVID-19 in urban areas. Derek, we are looking forward to your talk.
Okay, great. I think you can hear me properly, so I'll start presentation mode and then see if that indeed works as intended. Can you see my first slide?
Yes, very well.
Okay, excellent, very good. So good afternoon, everybody, and yeah, thanks a lot for joining for this workshop and for this talk in particular. Apologies for the slight date error at the bottom. But what I'm going to talk about today is simulating the spread of COVID-19 in urban areas. This is very much a collaborative effort in the context of the HiDALGO project, and also in collaboration with the Department of Computer Science at Brunel, and also indirectly with the National Health Service in the UK. There are contributions from all sorts of people, and I mentioned a couple of names here on the first slide. So in HiDALGO, originally we didn't have an application that would actually tackle COVID-19, but the reality was, of course, that there is a huge outbreak of COVID-19 worldwide, which has a huge impact on everything we do, and even this very meeting is being held online because of it. And in March, we received at Brunel a request from the National Health Service in London, from 2 trusts in Northwest London, to ask if there was any modeling work we could do to help them prepare for the emergency response, but also, sort of scaling back service provisioning after the wave, and also to try and learn what they could expect. How high would the curves go? How many people could be affected given different scenarios, and what kind of mitigation measures could work? We didn't have a code at the time, but we did have a migration code called FLEE, and we lifted some of the concepts from that code to develop a new code called the Flu and Coronavirus Simulator. And we started developing that basically during the first wave of the pandemic. And the aim of the code is to prepare for the emergency response, but also to mitigate the challenges involved in that frontline defense for hospitals in the COVID-19 outbreak. Although we were asked by hospitals to develop the code, we also think the code is very useful for regional authorities. So think of municipalities or city councils, for instance, because we are also able to model interventions at a very detailed level. But more about that later. What is very important is decision makers, either from hospital trusts or from municipalities, they need reliable and reproducible forecasts of the spread of COVID-19 in local regions, not just nationally, because the thing is, when you look at an outbreak of COVID-19 in most countries, it's very uneven across the country, and different regions have different characteristics. Some areas are more densely populated, some areas are very well connected, others are more isolated and self-sustaining. So the existing models that operate on the national level very often are not really appropriate for this local modeling that really captures, say, a catchment area for hospital. So our code is specifically geared towards supporting that, and we also have support for a wide range of interventions. The code is not very complicated, so it's very easy to introduce all sorts of different variations. So we support a wide range of different lockdowns, other interventions like social distancing, mask wearing, closing certain location types, only sending certain classes to schools, for instance. We also have support for different viral strains. This is quite recent, of course, with the emergence, for instance, with the B117 strain in the UK, but also other worrying mutated versions of the virus emerging in other countries. I think this is going to become an increasingly important topic. And the last thing we support are variations in the efficacy of vaccines. So you can have different assumptions there, but also variations in the rollout. Are you able to roll out the vaccine very quickly, very slowly? Are you going to prioritize certain groups, for example, people above 70 years old, or are you going to roll them out in a uniform fashion? All these variations we can support within our code. And it's also our desire to support that led us to developing and still to, until today, enhancing the code. Now, what we do for simulations and the forecasts we provide are not just about the code. The code is just a bunch of lines of Python text with input and output files, and it doesn't tell the whole story. What does tell more or less the whole story is something we call simulation development approach, and that consists of 6 different steps. So when we want to make a COVID-19 forecast using our flu and coronavirus simulator or FACS code, we go through 6 different phases. First, we select the situation. There will be a region and a time period. The time period can be in the past if we want to validate the simulation to see if it works correctly, or it can be in the future if we want to make a forecast. We can also have time periods that go from the past into the future, so that we have a little bit of both. Then the next step is to obtain data. So there was a question earlier, in the workshop, of course, during Sergey's talk about how we collect data. In the case of FACS, we don't collect so much data ourselves, but we do have validation data that is provided by the National Health Service. We use geospatial data, individual buildings that is provided by OpenStreetMap. We then have disease characteristics data that we lift and extract from the latest papers that we can find, and demographic data that we largely obtain from the Ordnance Survey, or ONS, within the UK. We use these data sources to then construct the model. The geospatial data we can extract automatically using a range of Python scripts, and the disease model for COVID-19 is more or less static, but we can make modifications in the input files if, for example, there's a new viral strain that's more transmissible. We also construct models around behavior patterns. These tend to depend on the age of people and also whether they're hospitalized or not. And these behavior patterns basically consist of how much time do different people spend in different locations under different circumstances. So, for example, by default, a 10-year-old child might spend, say, 24 hours in school, an hour in a shop, 3 hours in the park, and so on. But a 70-year-old will not spend 24 hours in school, might spend no time at all in school. So this changes by age. It also changes when there are interventions. So, for example, if schools are closed, then people obviously will not spend that time at school, but they will spend it at home. And likewise, if a person is hospitalized, they will be spending a lot of their time in the hospital and not necessarily in other locations like schools and offices. So that's all part of the model construction. Then in the model refinement, we introduce all our measures. So that can be different types of lockdowns, social distancing, location closures, and mask wearing, and a wide range of other interventions that I can't even think of at the moment out of the top of my head, but that we have implemented. I think there are about 20 in total. And those we all put in the model refinement step. Then all that together, we use to execute the simulation, and then we obtain results. We usually do multiple runs. We do multiple runs because the code is stochastic, so every run generates a slightly different result. But we also do multiple runs because we want to see how the code behaves with different assumptions, and of course with different types of lockdown or different types of vaccine rollout, for instance. So about the code itself, FACS uses an agent-based modeling algorithm, which means that every person within the simulation domain, the area that we model, is represented as a Python object. And the Python objects are grouped together in two hierarchies. So there's basically 1 to 4 agents that constitute the households, and then a house can constitute 1 or more households. The code is written in Python 3. And it is open source. You can obtain it from GitHub. You can also Google it. You will be able to find and download it. There's also documentation around it. And it's distributed under a permissive BSD3 clause license. So it can be used both in open source projects, but also for more commercial projects if people would like to do that. In terms of performance, FACS is able to model local areas. We normally use it to model areas of about 300,000 people. But in principle, you could try to scale that up to about 2 million households. It will just increase the runtime to start the simulation and to go through the different steps. As I mentioned before, FACS incorporates OpenStreetMap data directly into the code using several extraction scripts. Which is largely automated, but OpenStreetMap can have annotation bugs, and those you may have to iron out when you load the location graph. Here's a simple example of a location graph. So this is for the London Borough of Brent. Has a population of about 300,000 people. What you can see here are a lot of different types of dots. You see a legend at the bottom right, but essentially all the red dots are houses. And then you might, for example, see some blue dots, which indicate hospitals. You might see some orange dots, which indicate hospitals. And on the bottom right, you can basically see the 8 types of locations that we currently support when we model boroughs. We also have an adapted version of the code that models university campuses, and there actually we changed the number of location types that we support. Now, a very important part of epidemiological modeling is to get the properties of the disease right. In fact, we pay a lot of attention to try and realistically model all these assumptions. We have disease definitions for COVID-19 and for flu. And when there are new strains of COVID-19, we basically modify the definition for COVID-19. To give you an idea about the assumptions we put in the code, I put up this slide, which describes them. But I also just want to make clear that this is all stored in a YML file, so it's very easy to modify this for your own purposes. But in terms of assumptions, what is quite interesting is that we don't use an R number, but we model an infection rate. More on that later. And we have an incubation period of 3.5 days. That's not the period that people will start to get symptoms, but that is the start of the infection until when people become infectious, so they can infect other people. So that period is approximately 3.5 days, according to our understanding. And then we model two types of disease progression. There's a mild one, which is about 14 days to recovery and no hospitalization, and a severe tract where you have 20 days to recovery and where there is hospitalization and the chance that you might not survive the disease. The time period to hospitalization is on average about 12 days. And in our code, the mortality is actually not something we validate against or we look at a lot. We look much more at cases and hospitalizations because we work with hospitals. So at the moment, we use a mortality rate of 1.6%. But yeah, that is actually something we could adjust downwards given the evolutions in medical treatment for COVID-19. The mortality per age will differ, and you can see a graph of that in the top right. This is based on a paper published by Imperial College London that examined the data in Wuhan in China, but that too can be updated as and when needed with new values. So the duration of hospitalization is 8 days on average, and the period to recovery for mild cases is can be 8.5 days. Okay. In terms of the computational approach, it's not only the facts code that we use, but actually a combination of 4 different components that we require to do the simulations. So first of all, there's the agent-based algorithm, which I explained already a little bit, but which I will try to explain a little bit later on. Then the ABM algorithm is basically incorporated in facts, and that provides all the logic. But then we also need to have the input data supplied and the output data processed and aggregated. So we have a pre and post processing infrastructure for that. And then because we typically need 30 to 300 runs, and sometimes even more, we also need an automation toolkit to automatically deploy these simulations to remote machines, to execute them, and to do any post-processing and data retrieval on them. To do that, we developed the Fab COVID-19 plugin for the FabSim 3 automation toolkit, which I provided the URL for here on the slide. And then lastly, we need resources to actually run the models. So a single simulation can run on your desktop, so it's not so hard to test facts and just do 1 or 5 runs. But for larger numbers, I would strongly recommend using a supercomputer or a cloud infrastructure. At the moment, the facts code has not been made parallel yet, so it uses 1 core per simulation. But if you want to do a good analysis, you will need a large number of simulations. And the parallelization of the code is something that we do plan to do. Okay, just to zoom in a little bit on the algorithmic side of facts, how do we model infections? So I just wanted to say something about this, because a lot of the existing COVID-19 models do something that strikes me personally as something very awkward. And that is that they take a quantity that they call the reproductive number, they put that in their model, and then they generate the number of infections, and from that they calculate the reproductive number. So I always think that it's not good to put a quantity in your model that you're also extracting out of your model and sharing with other people. So we actually use a different approach. So first of all, in terms of the activities that we do in a time step, so one time step in facts is a single day. And every time step we go through 4 steps. So the first step is that we progress the disease. So people who are exposed to the virus might become infectious after the incubation period has started, and they might, of course, continue further to hospitalization, recovery, or mortality. Next, we check the household. So we check, okay, how much time do the people in the household spend with each other, and what is the likelihood that they will spread the disease within the household? The third step is to resolve locations. First, we check, okay, how much time do people need to spend at certain locations during a given week? And this is based on those behaviors that I mentioned earlier. So for example, a person might spend 30 hours in office in a given week and 1 hour in a supermarket. We then book visits to the different locations on the days of the week based on these needs, and there's a slight randomization in terms of timing, etc. And we make the duration of the visits according to certain standards. So a supermarket visit will not be 6 or 8 hours, but an office visit will be having that duration. And then we let people visit these locations. They visit their nearest location, meet up with other people that visit that location on the same day, and then we can calculate the spread within that space. The fourth step is transport, and there we calculate roughly how much time people spend in transit, and then we calculate infections based on the transport usage level. At the moment in the code, we don't model street interactions on foot, outdoors, with transport, but mainly inside vehicles such as the metro and bus. Now, as I mentioned before, a lot of people talk about the reproductive number. So that's basically the number of persons that an infected person will infect on average. And this has been a very important property. And indeed, a lot of codes use that as an input parameter and also extract that as an output property. That has some issues because, for example, with the new viral strain, B117, people don't really know how it changes the R number. So there are groups that are saying, oh, well, there's an additive component. That could be an increase in R between 0.4 and 0.9. But other people say, well, actually, that's not the case. It's a multiplicative effect. So you actually have to multiply the reproductive number. So if you want to model this and R is one of your input values, then you're quite stuck with doing one or the other. In our case, this is not the case. And what we model is actually a very different quantity. So what we have been digging up in the literature, and it was not easy to find, but we found papers about cruise ships, about jails and other highly constrained environments where some people were infected and other people weren't. And there we could figure out how likely it is that infection spread in very small spaces where people spend a lot of time together. And the metric that we defined is, well, we call it an infection rate. And it's the likelihood that one infectious person infects a susceptible person in a 4 square meter space. So 2 by 2 meters, say. And this is within a duration of 24 hours. Now, for the original virus, after having researched about 4 or 5 different papers that give indications towards this, we arrived on an infection probability of 7%. So it's 7% likely that the green person will infect the white-faced person in this household, assuming that the green one is infectious. With the new strain, this increases to about 10 to 12%. So we usually use 11.5% as a probability of infection. So, and the nice thing about this is that you can just reproduce this on the local scale and it doesn't refer to the R number. And the increase here is also not related to the increase in R number, but we actually scaled up this number by 56% because there is empirical evidence that the B117 patients emit 56% more viral particles than the ones that have the traditional strain of the virus. So that's where it comes from. So we can just bypass the whole discussion about the R number in this way. In terms of results, there are a couple of results I just wanted to show briefly. There are many more results, but I just wanted to give you an idea of what it looks like. So here's a validation and a forecasting one for the London Borough of Hillingdon. On the bottom left, you see, on the bottom graph, you see the number of hospitalizations over time with an uncertainty bound around it, as we ran, I believe, 10 or 15 different simulations. And the green line is the validation data that we obtained from the NHS Trust. In the top, you can see the number of new infections on given days in the simulation. And you can see that the variation in hospitalizations is much larger than that of infections because the number is smaller, so there's going to be more statistical noise. The green lines indicate some recent changes in terms of lockdown measures. The first vertical line is a lifting of the November lockdown. The second one is the start of a new type of lockdown, which was relatively light, and that was then intensified in the third line. And what you can see is basically that the case rate drops very rapidly until the end of March, because we expect that this lockdown will last until the end of March. And then when that lockdown is lifted, and we lift it completely, you see it spike up again. But then, interestingly, it starts dropping down again, even though there are no further lockdowns. And that has to do because in our code, we still have permanent immunity. And that is something that I basically want to update next, because I think it's now clear that people do not have permanent immunity to COVID, but that can actually expire after a given amount of time. In terms of hospitalizations, you see similar trends, but there is a clear delay. So we made this forecast on the 8th of December, and we forecasted a peak around the 10th of January in terms of new hospitalizations per day. And that also seems to align with the data, as in London, the number of hospitalizations per day is indeed decreasing now. Here is an assumption. So here's another forecast, which is slightly different. This is for Brent. So it's basically a different borough, but the same forecast. And I think what is relevant here is that in the bottom graph, you can again see the validation data. And you can see that for Hillingdon, we slightly overpredict, and for Brent, we slightly underpredict. But our algorithm is reasonably close to the validation data, as you see the green line straddling the uncertainty region of our simulation. Then we also can vary things, as I mentioned in the code. So for example, we can look at the effects if the vaccine rollout is worse than we anticipate, which you can see here. And what happens then is that essentially the lockdown will give a reduction in cases, but then it stabilizes. And when the lockdown ends, it shoots up even more than in the default case, where sort of the third peak is similar to the second peak. If you have a better than expected vaccine rollout, then essentially there's almost no third peak. But you also see a drop in new cases during the lockdown and a drop in hospitalization. So how well the vaccine works is actually something that we can observe in London by looking at the number of confirmed new cases, but especially the number of hospitalizations. So if we see the numbers of hospitalizations steadily declining over January and February, even though there are no changes in lockdown measures, then that could indicate that the vaccination is actually working better than people anticipate. And that could also make things less risky when the lockdown is lifted. Okay, the last slide I have is, of course, containing conclusions and future plans. So our code, facts has been validated, and it has also been used by 2 NHS trusts in Northwest London to support planning and strategic decisions. And I think that's quite remarkable, given the fact that there was not a single line of code at the start of March last year. But yeah, it has been used, and it's our forecasts so far have turned out to be pessimistic, but in retrospect, relatively accurate. The code also serves a public good, and we provide occasional forecasts to the general public. For instance, in the summer, there was a piece in the Sun and in Metro where we spoke about the second wave of coronavirus in the autumn that would shoot up less rapidly, but could still be very, very serious. And we also had a very recent article in The Conversation where we discussed the effect of school closures on COVID-19 spread. And there we essentially argue that school closures do affect the number of cases, but not in a very dramatic way. And we also think that the effect on the hospitalizations and deaths might actually be even smaller due to the vaccination program that is active within the UK. In the very near future, we want to incorporate non-permanent immunity. We've already started on that, actually. We want to parallelize the implementation so that you can run a single model across multiple cores. This is very important because it would allow us, for instance, to model the whole of London or a whole country within a single simulation, which is something we cannot do at the moment yet. And the third thing we want to do is to actually have more user-friendly forecasts. And the last thing I just wanted to say about that is that to try and get that going, we have a crowdfunding initiative going on in collaboration with the EU-funded VECMA project, where we essentially want to make an online dashboard where we can share COVID-19 forecasts for local areas with the public in general, and also make announcements about what we think people could be expecting. If you're keen to support this initiative, feel free to go to the website. I put the URL at the bottom, spsr.me/brec. We've got a range of update videos with details about specific features there. And yeah, of course, also the actual fundraising, as we're trying to raise funds to establish this dashboard. And that's it for me today. Thank you very much for your time, and I'm happy to take any questions.
So thank you very much for this interesting talk on a very interesting topic, a very hot topic at the moment. Any questions? I don't see questions in the chat. And I don't see questions here as well.
Yes, I can.
Excellent. It's also almost 3:10, so I think we can make a gentle start of the second session. I see that there are about as many attendees as during the last part, so I think many people have stayed in the call, which is very good. During this session, we will have two talks, one by Florian Ziemen from the DKRZ, and one by Fabian Dembski, who works at the Competence Center for Global Systems Science. And the first talk is about the ESiWACE project. So Florian is the scientific program manager of ESiWACE, I understood, and he will give a talk about preparing European weather and climate models for the Exascale. Are you able to share your screen, Florian?
I hope so, usually yes.
Okay, very good.
Are you able to see my screen?
Yes, it's all clear. I just wanted to check with you. Are you happy to take questions during the talk that people can type in the Q&A, or do you prefer to have them at the end?
I'll answer them afterwards, I guess.
Okay. I encourage people to type the questions in the Q&A during the talk so that I can gather them and then ask them to Florian. Or if a question is particularly detailed, I might actually unmute you and enable you to ask the question directly. All right, Florian, welcome to the workshop, and feel free to proceed with the talk.
Thanks. So yes, I'm actually representing the ESiWACE Center for Excellence, and I'm working at DKRZ. I have a long history at the Max Planck Institute, so I sometimes may mix up us in the meaning DKRZ, ESiWACE, or Max Planck. But you will see that in the talk. So a brief motivation why we're doing the whole work on climate. This is more or less the climate of the last 800,000 years, which is the time that we have really good carbon dioxide records for, because we can actually drill that deep into the Antarctic ice sheet and get ice cores that still contain old air. And you see an up and down in carbon dioxide between 200,000 and 200 and 280 parts per million concentration, sharp ramp ups in the deglaciation and glacials. And matching this up and down in carbon dioxide at this 100,000 year glacial cycle, you see ups and downs in tropical sea surface temperatures, in Antarctic temperatures, and in sea level. So sea level was going up and down about 100 meters between glacials and interglacials. And well, saying that's the last 800,000 years is only part of the truth, because it lacks the last 150 years, where we went up to here to 412 ppm. So we're really pushing the system way out of what it's been at in the last, well, time of mankind, more or less. And now we can run simulations for the future and ignore the purple line. So the bluish line here is the historical record reproduced in the climate models, or in the Max Planck Institute climate model. And green, orange, and red are future simulations under different emission assumptions. and they lead to a warming of about 1 degree above 1960 to 1990, which is already a good bit above pre-industrial, or more up to 3 to 4 degrees above that line. And so 3 to 4 degrees above pre-industrial would be about the same magnitude of climate change that we saw in the 10,000 years of the last deglaciation, just compressing that change in 100 years. So we're doing about 100 times the speed of the climate changes. And the good news is we're not going to get another 100 meters of sea level rise because there's not enough ice left in Antarctica to raise the sea level that much. But the bad news is we're still going to get a massive change in the climate. And we're going to see it in temperature, we're going to see it in precipitation. And we're going to see it in a lot of other things. So if we just take the end of this temperature plot and align it with the findings of the 1.5 degree report of the International Panel on Climate Change, we see that we're basically going to destroy all warm water corals. So this is pre-industrial climate. This is somewhere where we are right now already. And this is 1.5 degree, or this is 2 degrees. And this is like 3 or 4 degrees where we're heading right now. And so it's corals, it's mangroves, it's fisheries, the Arctics are changing at an incredible rate. I've done a lot of ice sheet modeling and working with glacier people, and everything in the Arctic changes rapidly. I spent a year in Alaska, and they build a lot of houses on the frozen ground there. And that frozen ground is thawing, and it's thawing way faster than we've predicted. So these houses are collapsing because their foundations are gone. And the glaciers are retreating. Everything is changing there at a crazy rate. Terrestrial ecosystems are going to get massive damages. Coasts, crop yields. A friend of mine is a farmer in the area right to the east of Hamburg. Well, she's a veterinarian, and she knows a lot of farmers, and they're totally afraid of more dry summers because that destroyed their harvests and the grass for the cows. So there's really a lot of changes already happening right now. They're going to be more severe at 2 degrees, and they're going to be way more severe at 3 or 4 degrees where we're headed right now. And that scenario is usually called business as usual. And at the moment, I'd rather call it apocalypse as usual, because calling it business as usual pretends we could go on living the way we've been, and that's just not true. So things are really changing. And some examples where we see it right now, here's a heat wave from 2019. Here's fires and hurricanes in the US. So you see the fires in the Western US, and there's smoke going all across the US. You see a whole bunch of hurricanes in the same satellite image. So on the same day, you see already 4 hurricanes. That is just not normal, but it seems to be the new normal. And so we have to get better at predicting or modeling these events in the climate models. And that actually means going to smaller and smaller scales. And that means we have to go to higher and higher resolutions. And this is a slide that I got from a colleague, Peter Düben. He works at the European Center for Mid-Range Weather Forecast. So they do the world leading weather forecast right now. And if you go to the small scales, they're like kilometer, 10 kilometers to kilometer. You get deep convection, which is really important for hurricane systems. You get tornadoes, and you get shallow convection, which is important for the clouds that have a massive impact on the temperatures in the tropics and thus on Earth. So we really want to get into this regime of this kilometer scale modeling, and that needs big computers. So that's where we will need the exascale computers. And weather and climate have a long history of running on the biggest computers we can get our hands on. So here is one of the grand people involved in ESiWACE, Newt, where they ran on the American Summit supercomputer. at the time when that was still, I think, top supercomputer in the world. So we're used to going for the big computers, but these things are getting more and more nasty to work on. So we need to put in effort for improving the codes for that. And on the other hand, when we do these models on these very high resolutions, we can actually get pretty close to real Earth in terms of the processes in the atmosphere. And so here's 11 pictures of Earth. And one of them is a satellite photo, and the others are model results from different models that are doing these storm resolving simulations at a couple kilometer scale. And 3 of the simulations are from models that are part of ESiWACE. And the whole intercomparison is strongly supported by ESiWACE. So we're collecting the output data from the different modeling groups. And we're providing this output at DKRZ to everybody, to all the scientists who are interested in analyzing this. And all in all, this is about a petabyte of data for those 40 days and a few models. And we're just doing the second phase of this intercomparison. So this was simulating 40 days in summer of 2016. And we're now simulating 40 days of the winter of 2020. So January through February of 2020. And this time coincides with a big measurement campaign near Barbados, where a lot of airplanes, ships, people on the ground, everything involved measuring just these shallow cumulus clouds in the tropics. Because if you just look at this, a cloud is basically white for the sun. The ocean is more or less black. So having a cloud or not having a cloud makes all the difference between the sunlight getting absorbed or not in the ocean. And that makes a lot of difference for global warming or for Earth temperature. And so of these models, the 3 ones that are part of ESiWACE are this, and that. And this is actually the satellite. And for me, it took a bit of getting used to them to be able to tell them that it's almost impossible to tell the models from the data. If you kind of know what you're looking for, you have a chance, but otherwise, they're getting really close. And that just, like traditionally, we have grids of like 200 kilometers or 100. And having this kilometer scale resolution and getting these storm systems correct, so useful for improving forecasts. So weather forecasting usually is a bit better than climate, because climate runs for more like 100 years and weather runs for more like a couple of days. But both will really benefit from getting to these exascale computers and getting these storms properly resolved. And so what ESiWACE doing there is actually just helping making these simulations possible in the whole chain. So we have a couple people looking into Silk as a workflow manager that controls how the model is running on the supercomputer. We have Earth System Data Middleware as a way of dealing with the big amount of data that these models produce. So it's parallel writing to the file system. And it's Object Store for handling the data. We're doing a lot of work with ParaView, which is a parallel visualization software. So you can run on a lot of cores at the same time on several nodes for your visualization. There's Catalyst, which enables visualization from the data straight from the memory of the model without even going to the disk. There's HPDA, which is a parallel data analysis and visualization software from the CMCC in Italy. So there's a lot of work on getting the big amounts of data that we generate to something that we can actually look at. And at the same time, there's work on improving the algorithms. So we're looking into domain-specific languages. There's 2 languages that are relevant in the climate domain, that's Cyclone and Grid Tools. And we actually managed to bring the people from these 2 languages together. So that's the European languages. And they are exchanging their work and building a system where they can move from one to the other. And we're also containerizing the model code, which for one thing helps porting them. And for the other thing, it actually helps keeping a stable environment for running the model. So when the supercomputing center does updates to their software, our model code still is identical in the running environment, so we can reproduce all simulations or continue them without changes in the underlying system, which is very helpful for the analysis, because otherwise you never know what changes from a new compiler, what changes from a new library, and what changes from actually changes in the model. And we're also reaching out to the community. We have a service from the Netherlands eScience Center in Bull ATOS, where they take other groups' codes. People can just apply for half a person year of consultancy, and they will help parallelizing their codes. And of course, we also do outreach and dissemination efforts in terms of trainings. So this is all stuff that's going on here. We're supporting 2 different ways of getting parallel data from the model into the file system with asynchronous I/O, so the model can continue running while other nodes are taken care of, or other processes are taking care of getting the data to the disk. Save a bit of time there. And this is our team. So we have the UK Met Office, the European Centre for Mid-Range Weather Forecast, ESiWACE, and the Swedish Meteorological and Hydrographical Institute as weather services. We have the French IPSL, the German Max Planck Institute, and Mercator Océan from France as more climate-oriented groups. We have Bull, DDN, and Seagate as hardware suppliers. We have ARMForge collaborating with us. They're not officially a part of ESiWACE in the second phase anymore, but they're still interested in working with us, so we still keep that contact. And then we have a whole bunch of teams doing support with Sergiy in France, University of Reading, Manchester University, UK Science and Technology Facilities Council, the Dutch eScience Center, CMCC in Italy, Barcelona Supercomputing Center, ICHEC, CSCS, and DKRZ, or supercomputing centers of different levels that are working on that. So DKRZ, we're actually a supercomputing center dedicated to climate. ECMWF and all the other meteorological services usually have their own supercomputers, the weather services. So it's all different groups getting together to work on this one task of getting these models to the bigger computers. And I'm not going to go through this again, but I'm going to go through the work packages now. And so in the first work package, we're really working on these models and working on the code of the model to get it better. So ECMWF, for example, is looking into porting their algorithms to GPUs. We're doing these intercomparisons where people can just look at the data, analyze it, improve their workflows, figure out how to actually handle data that is so big. And just by comparing the different simulations, we can start telling like what is a model specific thing, what's an artifact, what is actually common among these storm resolving models. And it really, the intercomparison needs the support and the disk space and the compute resources on the supercomputer to actually happen. And it's a bottom-up initiative. In the start, it was John Stevens from MPI and a colleague from Japan, and they decided just like, yeah, well, let's do this. And at the end, it's like, I think it's 9 teams that teamed up and all produced data, all produced these simulations, usually without specific funding for it, just because they really wanted to see what's going on there. And there's a lot of work on NEMO and the European Ocean Model on getting it faster and better on the computer. So it's really, it's the direct work on the existing models. And we see that we can scale to a lot of cores IFS, so the European weather model, scaling on PitStained and on Summit. So PitStained is the Swiss supercomputer. Nemo, the ocean model, and on Mare Nostrum 4. And ICANN, we got this HiQ thingy in 2015 for going on 500,000 Blue Gene cores. So we're really pushing the models all the way that we can, just to get these extreme resolutions where we can actually get into these storm systems and really see what's going on and model them better. At the same time, we know that just improving the existing codes bit by bit won't really do it for the Exascale system. So we're looking into the DSLs to get easier porting to different architectures. We're looking into concurrent components. So we're already modeling the atmosphere and the ocean in parallel, but you could model the radiation in parallel to the transport and start to go more and more parallel on all the different parts of the model. We're doing the containers, and we're also looking for emerging technologies like machine learning. So Peter Düben is doing a lot of work on that, keeping an eye on what's going on there. Then we have work package 3, which does these services for other teams. And we have the high performance climate and weather benchmarks that were developed in ESCAPE 2 or are being developed in ESCAPE 2, and that ESiWACE will continue to support. So when new supercomputers are bought or supercomputer manufacturers are interested in seeing how their systems perform for climate models, they can go back and use these benchmarks instead of running the full model. And just pointing at these services, on our webpage, ESiWACE.eu, under services, you can find the HPC user services. And we're really looking for people who are interested in getting help with their models. So if there's anybody who needs help with parallelizing their weather or climate model, please get in contact with us. We do annual calls, but we're also looking into other ways of finding people who could use a hand. And then we have the data handling at scale. So for one thing, storing the data. Also, we do these ensemble simulations where we start the same model up to 100 times from similar but not identical initial conditions and run them into the future. So that's a standard practice in weather forecasting. You start the model a little bit differently. You do a whole bunch of simulations, and then you can say, okay, we have 5 simulations that show rain and 2 that don't. So it's more likely to rain than not. And that's kind of the envelope of the things we expect. And now if you have 100 simulations that are very similar, you can, of course...
5 minutes remaining, just to let you know.
Should do. You can, of course, think about storing your data differently and storing the mean of these 5 simulations, and then just deviations from that mean, which are much smaller than the absolute values. And so that's part of this work package 4 effort in storage, and also making it more transparent for the user, so we don't have to worry whether data are on disk, on tapes, or on other media, and the system figures out where which data should go for now. And then there's work package 5, which I'm also involved in, which does the analysis and visualization software. And one part of those is this in situ visualization, and the other part is just working on the existing tools and standard visualization from disk. And so here's an image of wind speeds near the surface. And this is from the diamond into comparison, where we took the model of the German Weather Service. So the German Weather Service and for climate modeling, we both use ICANN, just in different setups. So we took their 2.5 kilometer setup for the atmosphere and our 5 kilometer setups for the atmosphere and coupled atmosphere ocean, and we ran them all for the same setting for the diamond into comparison, and use just a comparison of the fields that they produce. And you can really see how these storm systems are migrating here along the Antarctic circumpolar current, or storms here, more tropical weather. So for these simulations to analyze them, it's actually getting messy, because going around the Earth at 2.5 kilometer resolution means you get about 20,000 grid points. Now, if you want to see them on your screen, even if you have a 4K screen, you actually would need 5 of those next to each other and a couple above and below. So this is just to get a vague idea of the resolution that we're getting to. When I did my PhD a couple of years ago, I worked with a model setup where I had a grid of 90 by 40 grid points. And now we're talking about like 20,000 grid points in one direction. And so the standard approaches don't really work there anymore. And we really have to look into new ways of doing the analysis. For the outreach, next time, yeah. We have this work package 6 that, for one thing, does the contacts to praise and other European high performance activities. And for the other things, we do trainings on I/O and domain-specific languages. We just did a training. We're doing a training on C++ for high-performance computing soon. Oasis is a coupler that combines it does the interface between an atmosphere and an ocean model, so it moves the data from and back. We did a training on high-performance data analysis. In fall, we did a container hackathon last year. We're doing a summer school on HPC now. It's a virtual summer school. But we're doing all these things just to get as many people up to speed as possible with the new systems. And so in the whole European HPC area, we're kind of here somewhere between applications and infrastructure with center of excellence, just like HiDALGO is. And also, we're not the only project in weather and climate that is working on this stuff. So there's a whole bunch of European projects that are all working together. And we had a proposal for Extreme Earth as a flagship project that didn't happen, but Destiny is now the new European massive scale initiative for building a digital twin of Earth in weather and climate. And so this is upcoming, and we're looking forward to this system and to contributing to that. And that's it from my side. Thanks.
All right. Thank you very much for your talk. So are there any questions from the audience for Florian at this stage? So you can type them in by pressing the Q&A button and just typing them in if you have any questions. Florian, while the others type out a question, I have a very short question
Sure.
about the very start of your presentation. So you showed these predictions about temperature increase and rainfall.
Yeah.
I guess one question I have is, what I always see is 3 different scenarios, sort of the optimistic scenario, the realistic one, and the pessimistic one. But I always see a very big gap between the realistic and the pessimistic scenario. And the gap seems to be much bigger than the uncertainty bounds of the actual forecasts. Yeah, exactly here. I guess it's a bit between your blue rectangle.
Yeah.
So I was just wondering, is the code, I guess the code is, the simulations are very sensitive to temperature increase, but do you have any other explanations why that is?
Well, the thing is, it's actually, I fear it's not the distinction between the realistic and the pessimistic. I fear it's the distinction between the realistic and the 2 more optimistic setups.
Okay. Oh dear.
So far, we've always been following the pessimistic setups. Basically, we can, so the model, well, climate is sensitive to carbon dioxide concentrations. And these setups are labeled 2.6, 4.5, and 8.5, which is basically referring to the effect of the carbon dioxide concentrations on the radiation at the top of the atmosphere at the end of the century. And there's a whole bunch of different setups. So there's 2.6, there's 4.5, there's also a 6.0, which isn't shown here because it's just usually not considered as that interesting. And then there is the 8.5, which is like the worst case scenario. But Also not too
Are
unrealistic.
you implying that perhaps there should be a different selection of scenarios, and the worst case might have to become the baseline, and there might be a worse than worst case scenario possible now?
Well, there's always worse possible, but we really shouldn't go there.
Okay, yeah, I can understand why.
So it's the business as it's usually called the business as usual scenario because it is a continuation of current evolution, but we really should go somewhere between those lower scenarios. So, or even below those. And it's just there's little scientific interest in the scenario between yellow and red because it doesn't really give you any great new insights usually. So people always do the lowest and always do the highest, and then they choose one of the intermediate ones.
I understand. In the meantime, there's one question that emerged in the Q&A from Nuno Pereira. How do models take into account the role of clouds? Are they parameterized? If so, does it influence the final results in terms of temperature rise? And if not, do you model cloud formation and let the system evolve?
So there's it depends on the model setup. So there is parameterizations for the clouds, and of course the way you are parameterizing them has an influence on the climate in your model. So we tune the models to, well, usually the models are tuned so they yield a reasonable representation of the last 150 years. And that very much limits your freedom in choosing the parameters for these clouds, because if you make their influence on the climate too strong, you will not be able to get the last 150 years, or if you make it too weak, you won't. At the same time, there's other groups. If you run the really high resolution models, you can actually start resolving them. So people are doing that. And there's some research that has evolved in the last years that shows that the clouds might actually make things a lot worse in the future than we're usually expecting it in the climate models. So we might be in for more of a change than we were expecting, but that is still, I would say, open to debate.
Okay. Well, again, thank you very much for your talk. Where it's 3:40 now exactly, so we filled the time slots to the brim. Yeah, thank you very much, and I will then introduce the next speaker.
Cool. Sharing.
Yes. Feel free to go ahead. Let's see. Okay, just give me a second. So the next speaker is Fabian Dembski, and he is from the Competence Center for Global System Science. Part of BW HPC, and he's going to talk about resilient cities following the path towards sustainable development goals. Fabian, can you hear me?
Yes, I can hear you. Hello.
Hello, good afternoon.
Thank
Are you able to?
Yeah,
you're welcome. Are you able to share your screen?
Yes, I'm trying to. Wait a second, please.
Yes, we can see it. Very good.
Great. I'm trying to start my presentation. Does it work?
Yes, and the quality of the sound is very good. So feel free to go ahead.
Thanks a lot. So welcome everybody. Thank you very much for introducing me. Well, I'm from the High Performance Computing Center in Stuttgart and currently responsible for developing a competence center for global system science in the framework of the project BW HPC S5. It's a very complicated name. Well, let's focus on the global system science part on it. I'm from my background architect and urban planner, so I'm not a software architect, but an architect who is actually building houses and things like that. Yeah, so a little alien in a high performance computing center. So I will talk more about the applications, and the lecture of the talk of Florian Ziemen was really great for preparing and very interesting indeed. And this is more or less the idea of how to apply, how to bring research to practice, and how to reach goals. Yeah. The Sustainable Development Goals are, for example, a goal to achieve. There are 17 interlinked global goals designed to be a blueprint or to achieve a better and more sustainable future for all, developed by the United Nations General Assembly in 2015 for reaching the goals by the years of 2030. I'm focusing today more on the cities and urbanization topic, because about 50% of the population, global population, lives in cities. So cities have an enormous impact on the global system, and as complex systems, they are high performance computing can support to reaching these global goals. The Competence Center for Global System Science aims to support collaborations of specialists on a professional and technical level. It brings together high performance computing with researchers from various disciplines such as engineering, natural and social sciences, humanities, but as well as decision and policymakers and practitioners from different fields. So the idea is to form a link between researchers and high performance resources and also research, of course. The aim is to provide decision support and policy making, and to form the basis for improving decisions in economics, politics, and the civil society. So high performance computing becomes a major tool for addressing complex societal and scientific problems and topics. We are also collaborating since quite a while with the HiDALGO project. So we started end of last year officially to collaborate. The global system science topic in the HPC S5 project is focusing more on the supercomputers in Baden-Württemberg, in this state of Baden-Württemberg in Germany. So we are having a network of 4 different computing centers involved in this topic, and also other universities like the High Performance Computing Center at University of Stuttgart. I'm trying to show you some applications and some topics how we try to address kind of the citizens and decision makers and planners. For example, with the development of digital urban twins. Until today, the arena of modeling and simulation, digital twins have mainly used in the field of engineering, but not in the urban planning topics. And their implementations for towns is relatively new. So they are kind of digital representations of material or immaterial objects like machines of the real world. And digital twins enable comprehensive data exchange and can contain models, simulation, and algorithms describing their counterpart, including its features and behavior in the real world. So to enhance real life perception, they can also be implemented in virtual realities, as we do, for example, we call them virtual urban twins. We are visualizing them in virtual reality environments like in our cave at HLRS to enhance real life perception. The virtual urban twins are sophisticated data models allowing for collaborative processes and citizen participation. So the focus is on the communication of complex topics for a broader audience and for improving these processes. So they are, so to say, a subcategory of a digital twin, or rather an interface. So we are trying to making complex data accessible for all and finding a language for stakeholders of divergent disciplines for laypersons. So this can be cities, citizens, administration, decision makers, or politicians. And I will show you some smaller use cases we are working on. For example, a digital twin of the Hamburg region in Germany. It's in the south of Stuttgart. We worked together with Fraunhofer IAO in this case. This digital twin was focused on collaborative planning, participatory processes in virtual and augmented reality, and meant as a planning and decision support tool. So our focus was on open source, open access, and open data in this case, and also of the integration of citizen science, including socioeconomic data. It was also meant to support education and stakeholder engagement, so to say, inclusion. We focused on scales from the building level to the regional level. In the slide you can see the sustainable development goals we focused in this case. I will show you a short video. It's not so short. I hope it works. Wait a second.
We don't see anything moving yet.
Yeah, sorry. I'm trying to fix the problem.
Okay.
Okay. Do you see again? It's hopla.
I see a slight darkening of the screen, but no movement yet.
Okay.
I must say, videos over live stream connections can be tricky, so that's also why I'm paying extra attention.
So I skipped this video.
That's probably the best. Yeah, I don't see anything moving, so I think there's some codec issue somewhere.
I guess so. Just one moment. Can you see my slides again?
Yes, I see the slides with the video screen again.
Yes.
So that's
okay. So I switch forward. We have also project focusing on. We were also working on projects, or still working on a project focusing on the energy, the energy turnaround, Energiewende, how to improve so now I'm out of my context. So a focus on energy transition, on collaborative planning tools, how to make these energy transitions possible. In this case, in the Black Forest region in Vorbach in Germany, we made a digital twin for a pump power storage station in the Black Forest. So for saving energy and for simulating also for visualizing the process of this transformation. We used in this case, we try to, for collaborative planning, we are including all relevant stakeholders. So, for example, nature protection, NGOs, engineers, also management and finance. So we built this digital twin of this region for the EMBW, which is a power supply company, and for the powers for the power station, for the pump power storage, which is inside a mountain. They were they were using these tools for their engineers, but also for the citizens on site to help make them accessible, the contents. We have also the open source, open access, and open data approaches. We included also the topics of citizen science, so getting information from citizens who have local knowledge. We integrated simulation of noise, which you can see in the background, numerical flow simulation of wind and water flow, building information modeling data, and we're using this for education and stakeholder engagement. For example, during participatory processes, we had in total 1,000 people participating. So this is one of the few examples which could be, which is now in a realization project, because usually people don't like having big interventions. Here I'm showing you also a simulation of a dam break. So we could also simulate different hazards or different dangers, risks, to show people how for example, a worst case scenario, in a worst case scenario, a dam break could affect their environment and their lives. So here you can see that the city itself was not affected by the water in case of a dam break. And you can experience this in a virtual reality environment. Same as, for example, the construction noise and traffic noise simulations, and even the building and turbines are visualized in virtual realities. We are now starting a new project in Estonia, or we're trying also to support in the context of global system science a project of Tallinn University of Technology in collaboration with Aalto University, the Finest Twins project. Finest stands for Finnish Estonian Twins. This is a project which started now in January. We are starting. We are going to work on this, or we're going to support this in the following 2 or 3 years. And it's about the green and blue infrastructure, digital twin of green and blue infrastructure in Tallinn, Estonia. Even climate change affects northern regions, and this is one focus we are having in this case. Yeah, that's just one goal we are trying to achieve in the following month and year, to kind of create the basis for a digital twin there and to integrate our data here. Okay, there's something in my background here. Wait a second. Okay. There is something which is disturbing. Okay. Excuse me. This was not a YouTube link, which the video link which worked. At least the sound. And another topic is a project in Montevideo in Uruguay. We are trying to support, which should start maybe this year, together also with the Fraunhofer Institute, Fraunhofer IAO, focusing on digital planning tools for informal settlements, and also in collaboration with the Universidad Tecnológica in Uruguay, and yeah, with a focus on poverty, how informal settlements, how digital tools and digital twins could support also the development in informal settlements and improvement, for example, of the water infrastructure or infrastructure in general, and how to involve people in these processes. Yeah, another project is Open Forecast, where we are involved. My colleague Leila Kern is working on this project, a high-resolution 3D model of Stuttgart, which is focusing on air quality, and also using a weather and climate model, which is focusing on atmospheric calculations to model current and future concentrations of heavy particulate matter, nitrogen dioxide, and other pollutants. And this is in collaboration with climate scientists from the University of Hohenheim in Stuttgart, who ran these calculations on the HLRS supercomputer Cray, the former system which was called Hazelhan. And here you can see the cave. That's what I was originally wanted to show you, how a participatory process can function in a virtual reality environment. A cave is a cave automatic virtual environment where several people can participate at the same time. This supports collaborative processes and also participation. So it's kind of a translation tool. It's much easier to see this complex data like wind flow or emissions in a three-dimensional view, in a three-dimensional perspective, and also to choose your own path and perspective inside this model. And yeah, it would be quite difficult to explain these data in a two-dimensional way. So yeah, I'm at the end of my presentations. Sorry for the little problems, and thank you very much.
All right, Fabian, thank you very much for your talk. Apologies on my side for the slight change of scenery. I expect kids to come into the house soon in these lockdown days. But no, that was an excellent talk that covered a very wide range of digital twins and applications, as well as really nice visualizations. I guess the word is now to the audience. Does anyone have any particular questions or answers? Sorry, any questions or comments they would like to post? If so, please put them in the Q&A channel. So let's see what happens with that. All right. I guess in the meantime, I guess I have a very straightforward question for you. So you've shown quite a few different ways in which you can visualize this kind of geospatial data. And I think especially, for example, also the 3D visualization, a very nice way to make people explore detailed data in a much more rigorous and systematic way, because plots can be biased. It would be interesting to read some research actually about that, how plots can bias interpretation compared to actually exploring the data in a more immersive environment. I was just wondering if there's one very clear practical benefit that you've experienced while managing this project or in prior efforts. Is there a particular practical benefit that you think is worth highlighting?
Yes, thank you very much, Derek, for the question. Yeah, from my point of view as an urban planner, it was quite impressive to see how a very heterogeneous group of people can be involved in these processes. So I think it's very important to reach, for example, climate goals or urban sustainable development goals, or what goals ever. Also small scale problems like building processes, to involve all different stakeholders. So usually there's a huge gap in communication because of different expert languages and different expert knowledge. So even during the planning processes and the creation processes, it's very helpful from the beginning on to have different stakeholders involved and to find the same language, which comes through virtual reality and visualization, of course. And also, interestingly, the different participants from citizens, like citizen participation was quite impressive to have a very heterogeneous group. Usually, only few stakeholders are involved, or few people are involved. The classical white male and elderly people, so virtual reality, we were installing, for example, our virtual reality environments directly on site in the cities. And so it's kind of a little circus. It's like a spectacle. People like spectacles, so they came and were automatically involved in this process. So we had kids, we had elderly people, we had also people which were disabled, so they couldn't hear, for example. The deaf people, they were the first time involved in these processes, and they could involve in planning process. So that was quite interesting.
Okay, so really this evidence of sort of broadened participation.
Yeah,
I think that resonates a lot with me as well, because papers and plots don't convey very effectively to a broader public, and very often people don't raise questions and ask for more information or clarification. Usually people just detach from the subject at hand.
yeah.
So that sounds like a very useful added benefit. In the meantime, I got a few questions in. I got 2 questions for you, and we have roughly 7 minutes remaining. After that, we have 10-minute break, so should be doable. The first question is once more from Nuno Pereira. He asks, do you plan to upgrade your virtual reality platform information with Internet of Things platforms available in the future to get information from say, traffic and air quality for real-mode visualization with augmented reality? Available for citizens on a daily basis? There's a lot to unpack in that question, so go ahead.
Yeah, let me try to answer these questions. Well, in the example of Hamburg, unfortunately, I couldn't show you the film. I will try to send you the link later, so you can see it on YouTube. And it's without sound, but I try to explain it right now. In this very small scale digital twin of Hamburg, it's a small town. We try to integrate, for example, data from particulate matter sensors. So there are these low budget particulate matter sensors people can build themselves, or they used these sensors. So we try to involve these people and using the data almost real time to integrate it in the digital twin. So these sensors are out there and we can access the data. So temperature, also the PM 2.5 and PM 10. So that's, for example, one test we made kind of for integrating these data. We also tried to develop a small mobile application, which is more a fun thing, or it was kind of a test balloon. We had 30 young people using just a small group, so it was just a test balloon. 30 young people for evaluating public space, for showing georeferenced data. For example, their traces, how they're using spaces and places, which places they like and which places they don't like, where they feel fear, for example. We also want to integrate, traffic data and to integrate kind of other data provided usually by the city, by the cities. In Germany is quite difficult because it's really hard to access this data, and because of data protection is kind of the most important word in Germany, I guess. So it's quite difficult. Yeah.
All right. Yeah, excellent. I think, well, Nuno, I hope that that answers your question. I think it does. I must say data protection in the UK is completely unclear to me at the moment after Brexit, but that's a topic for another day. We've got another question from Vincent Tableau-Roche. Yeah, I think Nuno is happy with the answers. He says, excellent, congratulations on the work. And Vincent asks, isn't creating digital twins visualization a very time-consuming process? And are there any tools that could help make this process more widespread? And I guess with that, he means also easier / faster.
Yeah, that's a very good question. Yeah, the creating digital twins is the visualization of virtual twins is a very time-consuming process indeed. I know, for example, the Vorbach project. Uwe, my colleague Uwe Wössner, he is working on this project since I think 11 years, and of course these processes are never over, and you always have to integrate new models or visualize these models, which is a lot of work. Yeah, there would be it would be really there is of course there's a gap in how to a research gap kind of, or this could be quite interesting research, how to make these processes easier and faster. But I'm afraid that some of these processes are quite hard to integrate, because yeah, you get different. You're dependent on different sources of data. You get data, for example, from architects, but at the same time from the city government or from satellite data. So it's always a lot of work, and there it would be interesting to kind of find something to create tools that could help make this process easy accessible. Yeah.
All right. Yeah, I think I can chip in a comment or two in response to that question as well, as I'm actually developing an automation toolkit myself, which is more geared towards computational workflows. But I think, Vincent, one issue with automation software is the benefit is often invisible. Because when scientists write up a paper about data processing, simulation building, etc., what they usually don't put in is how much time they spend to get the whole thing up and running. And this is tremendously annoying from my perspective, because if you make an automation toolkit and you do something 10 times faster, so you save 90% of human effort, it's almost impossible to measure because nobody actually records it. Nobody has systematic logs about the activities that they do. They don't curate what they're doing. So actually writing a pitch for a paper that reduces human effort rather than compute time is incredibly difficult. And a lot of reviewers tend to misunderstand at least the papers that we write. And we also just find a lot of difficulty in writing it up. I think this is a very fundamental problem in the field. And that's why people always like to see seconds to completion of the computer program rather than seconds or calories to completion for the humans, because the human side is so much harder to measure and is so much less systematically measured historically. I think if we were actually able to expose that a bit more clearly, then people would also be more incentivized to try and build these automation tools. Is that a fair statement, Fabian, from your perspective?
Yes, you're completely right.
Okay, just to finalize it all, Nuno left a very small comment saying edge computing with a smiley. And I think that concludes this particular session. So we'll have a break of approximately 10 minutes, just checking my clock. So 20 past 5 European time, 20 past 4 UK time, we'll proceed with the last session. Sergiy Gogolenko will be the chair of the session. And we'll have one talk by Christoph Schweimer, followed by a panel discussion to sort of finalize this workshop. So I hope to see you all then. Thank you again very much for your talk, Fabian.
Thank you very much, Derek.
So hello everyone again. Welcome to the last session of the workshop for tackling global challenges with HPC and HPDA technologies. In the first talk of this last section, Christoph Schweimer from No Center will present road pruning algorithm for location graph extraction. Christoph, are you ready?
Yes, I will start sharing my screen.
Okay, please go on.
All right, I hope everybody can see my screen and hear me well.
Yeah, we do.
Okay, then thank you very much for the introduction and also good afternoon, or I would rather say good evening from my side. Today I am giving a presentation about one artificial intelligence component in the HiDALGO project, namely a route pruning algorithm for location graph construction. And this work has been a collaborative effort with a lot of partners within the HiDALGO project. At first, I want to give a short overview over the use case and where artificial intelligence is supporting the workflow. Then I want to present the AI component, show some of the results that we obtained and also some visualizations, and in the end, give a short summary. At first, the migration use case in the HiDALGO project deals with the simulation of forced migration of refugees, which is being done with agent-based models. And the simulation is being executed by one of our HiDALGO partners, the Brunel University. Some of the goals of this use case are first and foremost to save lives by supporting NGOs and governments such that they can assign humanitarian resources to the right places, mainly refugee camps. Another goal is to help complete the data collections on refugee movements but also investigate the consequences of border closings for refugees. The use case needs, amongst other things, as input a graph structure. And in this graph structure, the nodes correspond to physical locations. The edges of this graph correspond to direct routes between the locations, and the edge weights are the route distances between the locations, which are also being used as meta information. And in earlier times, these so-called location graphs have been created manually. And this manual creation is a quite error-prone and time-consuming process, as you have to compare for each location pair. You have to look at the route between the two locations and see if the connection is indeed a direct connection. And due to this error-prone and also time-consuming process, the size of these location graphs has been limited to approximately 50 locations. And now, with the support of artificial intelligence, we are able to automatically create these location graphs, where we can now create them with 10,000 and more locations within just a couple of minutes. And next, I want to give a short overview over the component. It starts with a list of locations that are given with their GPS coordinates, or alternatively, if a list is not given, we can also extract locations either from a country or a region from OpenStreetMap. In the next step, we are computing the fastest driving routes between all pairs of locations with the OpenStreet routing machine, which is basically giving us a fully connected location graph. And in this location graph, there are certainly a lot of indirect routes, and an indirect route in our case is a route where when you go from one location to another location, you're going through a third location somewhere on the way. And the goal is now, with our route pruning algorithm, to remove these indirect routes from this fully connected graph. And this is being done with the triangle inequality. And in general, route pruning corresponds also to network simplification, where some work has been done in the literature already. In this publication, the idea of the authors is to prune edges from a graph while they are still preserving the maximum path quality metric. And they are presenting 4 algorithms where the static triangle version of the algorithms most closely resembles our approach. These 2 algorithms have some shortcomings. The iterative global one has a high time complexity of big O of k to the 4th times the logarithm of k, excuse me, where k is the number of nodes, or in our case, this would translate to the number of locations. And for the static triangle approach, this does not guarantee a completely pruned graph. And with our approach now, we have a time complexity that is just cubic in the number of locations. It guarantees a completely pruned graph as the result, and we are also introducing a hyperparameter for flexibility. And next, I want to go more into the component and start with the setup. As mentioned before, we are starting with a list of k locations, and they are given with their GPS coordinates in latitude and longitude. In the next step, we are creating the directed, fully connected location graph, such that every of these k locations is now connected to every other connection via a direct route. And at this point, we're making 2 assumptions to simplify our approach. The first assumption is that the distance between a location in itself is equal to 0. And the second assumption is that we say that the distance between one location and another location is independent of the driving direction, such that we now basically have an undirected, fully connected location graph. Our approach would also work on a directed graph, but with the undirected graph, we are speeding up the approach and basically just simplifying it. At next, now we are at this fully connected undirected location graph, and the goal is now to prune edges from this fully connected graph that correspond to indirect routes. And again, an indirect route in our case is a route where when you go from one location to another location, you go through a third location. The first step of the route pruning algorithm is the creation of a copy of the fully connected graph. I will come to this in a minute again. We are then iterating over all ordered triplets of location. This means that we are basically just looking at a triangle of locations where in each corner of the triangle we have one location. We are then looking at each triangle individually and define the length of the longest side of the triangle as the distance between two locations A and B, and the other two sides of this triangle as the distance between A and C and the distance between B and C respectively. At this point, we want to try to prune, or rather, we want to remove the side from A to B from the fully connected graph. And for that, we have a pruning condition. And the pruning condition says that if the distance of the longest side is bigger than the sum distance of the two shorter sides, multiplied by a parameter beta, where we have that beta is smaller than 1, we prune the route from A to B from the copy of the fully connected graph. And here it is important to mention that the pruning happens on the copy of the fully connected graph, and that we are checking the pruning condition always on the original graph. And this is important because if we did the pruning on the graph, where we are also checking the pruning condition, then we might end up in a situation where we prune a route that is the longest side of a triangle in one triangle, but might be a shorter side in another triangle, where the algorithm would usually prune the longest side, but due to the fact that it already has been pruned in an earlier step, we cannot prune it anymore from the fully connected graph. And therefore, as mentioned, we are always checking the pruning condition on the original graph, but we are pruning on a copy of the fully connected graph. And with this beta being smaller than 1, this allows us some flexibility with the triangle inequality. Because in most cases, it would happen that the distance between two locations is smaller than the sum distance of the two shorter sides. But when we have a situation where we go from, let's say, to stick with the example, from location A to B, and location C is between those two, but because the locations are given with the GPS coordinates, we are not driving directly by the given coordinate of the intermediary location, but we are driving through the location within its city boundaries. We would eliminate this route from the fully connected graph if we did it manually, but the algorithm would not detect it, such that with this beta being smaller than 1, we are relaxing the condition of the triangle inequality and can remove routes with these instances. And when we are done with iterating over all ordered triplets of locations, the output is then the undirected weighted location graph of direct driving routes, exactly what we want to have. And next, I want to visualize our approach. We are starting here with an example in the federal state of Syria, where we have 15 locations in a region. And I have omitted for this plot the GPS coordinates for visualization purposes. In the first step, we are creating the undirected, fully connected location graph. And here in this plot, we already see the undirected graph. In the background, in blue, we see the fastest driving direction, and each location here is connected to each other location. At this point, we are applying our pruning algorithm, and we have done that for several values of the pruning parameter beta. And here's the result for beta equals to 0.9, where we can see that a lot of the routes have been eliminated. For example, the most eastern location is Hamburg. In the fully connected graph, we had 14 connections for this location, and now only 3 connections are left. And we have also done it for beta equals to 0.95, where you can see that here we have just a couple of more routes being left from the fully connected graph after applying the pruning algorithm. We have in total applied our pruning algorithm to 4 different regions of different size and road infrastructure, 2 small regions in Europe and 2 bigger regions in Africa. Here we can see the results that we obtained, where we created the ground truth of direct driving routes manually, which basically corresponds to what I said in the beginning, the manual creation of location graphs. And in the 5th column, we see the algorithm routes result, where we see that in some cases we have more than the ground truth routes, and in some cases we have less than the ground truth routes. In general, we observed that a value of beta between 0.9 and 0.95 returns the best results for us, and that bigger values of beta, or for bigger values of beta, more routes are being kept from the fully connected graph, and for smaller values of beta, the algorithm prunes more routes. And what we can also see here is that with our approach, we got an F1 score exceeding 0.9 in 3 of the 4 regions for 2 different values of the pruning parameter beta. And next, I want to show another visualization that we created, again for the same region in the federal state of Styria, where we see in the background the fastest driving routes between the locations. In orange, we see the direct connections that we obtained as the ground truth of direct driving routes, and the black dashed line is the result from the pruning algorithm, here for beta equals to 0.95. And here we see in this visualization that we have a really good overlap of our ground truth and the result that is being returned by the pruning algorithm. To summarize, we developed a computationally very efficient route pruning algorithm to create these location graphs. We are able to reduce the location graph construction time. For instance, in the South Sudan case study, where we had 93 locations, it took several days to create the ground truth of direct driving routes. And with the algorithm, this was being done in basically just 5 minutes. So we are really able to reduce this time by a lot. We have also introduced a tunable pruning parameter such that our results can be customized, where you can set it higher such that more routes are being kept from the fully connected graph, or you can set it to a lower value and more routes are being pruned from the fully connected graph. We have also observed that longer route distances can be problematic, and also when 2 locations are close to each other, it can be problematic for the algorithm. But these 2 shortcomings are also shared with other algorithms that we saw in the literature, such that we can say that we really achieved good results in the 4 regions where we have different size and road infrastructure. And we believe that our approach can not only be used as an AI component here in the HiDALGO project for the migration use case, but also for other agent-based model simulations or various logistics optimization problems. For further information, we are currently in the process of submitting our findings and our development to Nature Scientific Reports under the name A Route Pruning Algorithm for an Automated Geographic Location Graph Construction. And with that, I want to say thank you very much for your attention, and I will gladly answer any questions.
Thank you, Christoph. If anyone has the question, they are welcome to post them to chat and Q&A. So far, I do not see any. As one additional question from my side, Christoph, I want to ask, you said that this algorithm is applicable to migration use case, to the simulation of migration of people and so on. But can you predict any other applications for the algorithm besides this simulation of the migration of people and agent-based modeling in general?
Yes, thank you for the question. We believe that in various logistics optimization or traveling salesman problems, this algorithm can also be applied. When you, for example, try to find the fastest route from one location to another location, and you have just a lot of roads. With that, we can simplify this network. And we haven't checked yet if it can be applicable to other problems, but we believe that in those traveling salesman problems, it can also be used.
Okay, thank you, Christoph. Well, in case there will be further questions in the audience to this talk or former talks, everyone will have an opportunity to ask during the round table, and right now is the time of exactly for this round table. The discussion will be facilitated by Elena Gonzales from ATOS. Elena, are you ready?
Hello, I'm ready. So
yeah, okay, then I hand over the, yeah, we can hear you. Then I hand over the mic to you.
Okay, thank you, Sergey. So thank you for all these really interesting presentations that we have seen before. Now we are going to start at a round table to talk about the addressed topics, but also to exchange opinions among the speakers of the presentations. Of course, I encourage to the audience to send your questions to the chat or even to raise your hand, and I will tell your questions or even I will give you voice. So let's start. All the speakers can hear me, I guess. Sergiy, Robert, Christoph, Florian, Derek, and Fabian. Okay, thank you. So, well, first of all of you have presented different technical solutions that can be used to tackle global challenges. I would like to ask you, how do you think that these technologies, artificial intelligence, HPC, HPDA, can support the achievements of these goals? Or in other words, what is the added value of these underlying technologies to solve the global challenges? So any volunteer would like to start? Well, on my left, I'm watching to Florian. Maybe put to mind to tell us.
Well, I think in general we can make predictions or forecasts a lot more precise and specific by using the HPC technologies. Mm-hmm. So in the case of weather and climate, it's been known pretty long that, so it's been known for more than 100 years that if you double CO2, climate will get warmer by something between 2 and 4 degrees. And we started with the coarser models, but if you talk to, let's say, a farmer in Germany, they will want to know, okay, how is the weather going to change in my place? How are the droughts going to change in my place? Which trees can I grow in this situation, or which plants? And for that, you really need the high resolution models that actually get down to this resolution where you can say, okay, in this region, we see this is going to happen, and not just, well, globally, it's going to be warmer and it's going to be a bit more precipitation in some times. And I think it's this extra bit of precision where you actually get down to like regional scales where you can say, okay, we're going to see these extreme events in this way or that way changing. That's where we really gain from the high resolution, and that's where it becomes really relevant for decisions, especially in adaptation.
Okay, so the difference could be very accurate predictions in local regions that currently, I guess that they are not feasible with the current technologies. Okay, any other speaker would like to add something?
Yeah, I'm happy to do so. So yes, I completely agree with Florian. The forecasting is very important. People know what to expect, and if something bad is bound to happen, people have an advance warning about it. It also eliminates the wasting of resources. So if you think about health, medical resources, or perhaps food and shelter, in the case of migration, for instance, then accurate, reliable forecasts with good uncertainty quantified around them can help organizations to waste fewer resources and put their resources where they're needed the most. So I think that's very important. And I think another role is societal awareness. So for instance, when conflicts occur with migration, I take that example, some countries choose to close borders and people don't necessarily think about the consequences of a border closure, but they can be quite severe. And with simulations, you can try to characterize those kind of forecasts. Similarly, with COVID-19, governments can choose a different kind of intervention. What would be the consequences? So I wrote a piece in the conversation about school closures, but there are many other interventions that you could think of. So those what-if scenarios are very useful as well for public awareness also, so people can account politicians to some extent for their choices. And the third one is a bit more niche, but sometimes it's very hard to collect data. So again, especially for migration, it can be very hard to figure out where people are. Where are the refugees? And we see the number of refugees on the UN website, and we take that as the absolute truth. It is not. They have huge problems collecting these numbers. Sometimes they have to make estimates, and these models could help a little bit with that as well. So we can actually get a slightly better idea about the exact magnitude of a conflict and how many people have had to flee their homes.
Okay, thank you, Derek. So expectations about these technologies are really spectacular, really terrific. Derek, you have presented the COVID use case that it's on the news the whole day, but all of us expect that someday COVID will be history. So it is possible to replicate this type of models to different scenarios, to different situations?
Yes. So first of all, I'm afraid that the battle, we might have a victory in the battle with the vaccines emerging, but I think the war, so to speak, is not over because the virus is mutating. It can mutate, and there are some very worrying signals from Brazil, for instance, where the virus seems to be partially resistant to some of the vaccines. That is all very preliminary, so we'll have to see. Let's hope it's not as bad. But the code can also be repurposed for flu and other types of airborne diseases. So we have made a disease definition for the influenza, for instance. So if there is a future outbreak, we could repurpose the code for that. What we haven't incorporated, for instance, is things like service transmission. So for that, we would really have to rewrite the code. But if the need really arises, I mean, we wrote this in quite a short time span as well, so it is possible.
Okay, thank you. So I would like to formulate to the rest of the speakers the first question. For example, in my screen, I can see Fabian, the next. I remind you the question is how do you think these technologies can support the achievement of the exposed goals related to the global challenges?
I think if we're talking about technology and we're talking about...
Well, sorry, mainly technologies, HPC, HPDA and artificial intelligence.
Yeah, but the question in general is, as Derek just mentioned, the situation, for example, in Brazil with the mutation of a virus, and we can develop tools and we can develop technology, but the question is, technology is not a solution per se, so it needs kind of the political will and also the societal agreement in these topics. And I think this is a very important thing to work on, to get more acceptance for scientific approaches and for technology development, also in the political sense. So I think this is going, maybe this pandemic is a chance also for getting more attention to the scientific community and for the development of these technologies and tools for solving problems or for helping solving problems. But problems can be solved, of course, by technology itself. So it's a human problem.
Okay, thank you, Fabian. And you have presented the use case related to resilient cities. It's possible also in your case to replicate these to different scenarios, or it is still too early?
Yeah, we're trying to do so. So we are trying to make this in future projects. So yeah, of course, this is the goal, but it's of course complicated. But we are trying to do so.
Okay. I think there is a question of the public. Okay, I'm going to read this. Many of your projects require a lot of computational power for simulations and whatever. Have you already tried using hardware acceleration for your projects? That means GPUs, FPGAs, and if not, why? I have to understood the question, or maybe I can repeat it, or even
Elena, I think if you like, I can give an answer to the question.
Yes, thank you, Derek.
Yeah, so essentially the question centers on using dedicated specialized hardware components, which make the time to completion for simulation shorter, so it makes simulations faster. But there is a trade-off. The trade-off is that your simulation completes faster on a computer, but you spend more time developing it, unfortunately. And if you have a code, say an astrophysical code that I worked on during my PhD, that is based on Newton's law, that doesn't change a lot in time, then it's a very favorable platform to do your simulations on, because you make an algorithm rule set, and it can change in the case of cosmology, for instance, but it doesn't change so radically. It's not like the laws will change. But in the case of global challenges, and I'm not sure if the other speakers agree, we tend to model human behavior in many cases, and human behavior is often not so well characterized and also very much subject to change. And in the case of epidemiology, I think we all have read in the news how the virus adapts to circumstances, how governments continually come up with new types of lockdown measures, and all of this requires code changes in order to be modeled. So the real bottleneck we have is not so much the fact that the simulation takes a day to complete, or even 5 days to complete using 2000 cores. Now, the real challenge we have is that every time there's this little change, we again have to go back to the code, modify the algorithms. So in my group, we use Python, because that for us gives us the shortest route to make these modifications. And using dedicated hardware would impose an overhead in our case. But I think other speakers may be elsewhere on the spectrum between a lot of rule changes and long-running simulations with solid underlying assumptions.
Okay. Thank you for your detailed answer, Derek. So I would like to continue with Sergiy Gogolenko, that at the beginning presented HiDALGO project. I would like to ask you, do you think that general public is aware of these kind of solutions to solve real-world problems? what is the perception of the general public about this type of technological solutions that are so with such a high potential to solve the global challenges?
Well, in my opinion, general public is not, in general, it is not very aware, very keen on knowing much about the technical solutions which are used behind different simulations which we do, or which we use to resolve to design different policies and predict the effect of different policies. But the main the main thing that the general public is focused on is probably the results which different solutions convey. They are not much interested in what's behind them. So, and this is understandable, and yeah, I think it is the way how it should be. So people should be interested in the results, not in the solutions which are behind, and what is the general effect of this.
Okay. Anyway, as Fabian has mentioned, with this pandemic, I think the general public is more focused on the work of the scientists and the technological and scientific solutions to solve the humanity problems. Okay. So I would like to ask to Christoph, Christoph Schweimer, about your presentation. So do you think you can reach the same level of maturity and success if you wouldn't use this type of technologies, HPC, HPDA, artificial intelligence?
I would say we would not be able to reach the same amount of success as presented. We were able to reduce the creation time for these location graphs from basically a couple of days in some instances to just minutes. And if a conflict comes up very, very urgently or very quickly and the solution is needed, then you cannot really spend a couple of days just creating this location graph. And with this component, we can definitely reduce the time for the simulation and also finally see the outcome from a couple of days to, as mentioned, maybe a couple of minutes or hours. Also, in some of the other use cases of the project, the AI components are being used as enabling components for pre-processing, such that the relevant data can be used immediately, and we do not have to use any data that would be unnecessary for any kind of simulations.
Okay, thank you. All of you have the same perception than Christoph? Okay, I guess so. I think it's a similar line. Okay, so well, another question that I would like to formulate to you is that I think there is a general perception about the huge gap between scientific and technical communities and global challenges communities. So I would like to formulate this question to all of you. What do you suggest to the second one to get near the solutions provided by the first one? Okay, to make closer these both communities, scientific and technical and global challenges communities. Someone would like to start? Okay, I choose. I will start again in order. I see on my screen the first one. Florian, again, please.
Well, I think if you look at climate, for example, just by providing the data on the very fine scale that actually people need for understanding the effects on their specific locations, we're making it much easier to communicate with those communities that then have to see, okay, this is what climate change brings, and how can we work with this? And what are the effects for the people? And I think it's probably similar with the other teams, just by getting from, if you look at COVID, by getting from some R is 3 information to, okay, this is your borough stuff. I mean, that's.
Okay. So, Derek, do you agree with Florian about how both communities could be more aligned?
Yes, largely. I think there are some communities that actually are quite easy to align. For example, when you talk about pandemics or perhaps about weather and climate, because the jump from simulation to the reality is relatively short. I think in other cases it's further removed. So for example, if you're looking at things like political tensions or other things that are more in the humanities area, the link is harder to establish, and it's not as simple as just building a model and validating it. And there it's much more challenging to connect it to communities. So it's not easy everywhere, but yeah, I think in broad lines I do agree with Florian.
Okay, thank you. Fabian, what do you think?
I agree with Florian and Derek.
There is no debate here. All of you agree.
Yeah. But I think in general, it needs also it needs more communication and more finding the same languages and focus on science communication. The problem is that we are sometimes too focused on our own disciplines, and I think and writing papers for our communities, scientific papers, high-ranked papers.
Yes.
Following our careers, that we forget who we do these things for.
Okay.
And I think I think it would be good to just kind of find a broader communication channels and to get kind of that's also something which I discovered during this pandemic. That many scientists go to, I don't know, for example, YouTube, and also this open university approaches to get kind of information widespread. And this also helps enhancing new collaboration between very different disciplines. So I think that's a very important point.
Okay, thank you, Fabian. So, well, I guess that Christoph and Sergiy also agree. So I think I'm going to read a question from Nuno Pereira. He's asking, what is your perspective on quantum computing for the near future and the possibility of a general purpose? The merge of QC plus AI plus HPC would allow a scale up of the problems. Would you agree? I'm going to copy this for you. Okay, you can read the question in the chat.
I'm not sure if there are any experts on quantum computing in the room.
Okay, maybe it's a different topic.
Not entirely. I mean, I can give an answer, but my experience is very limited. So I would only do that if others do not feel confident to give an answer at all. So please.
Well, just looking at our codes, which evolved over like 10 or 20 years for a model version, and the effort we're currently putting into getting the code to run on the GPU, which is technically still very simple, similar to a CPU. Getting the whole thing running on a quantum computer, I think it would of course be cool, but I fear until this actually works at that scale will take quite a while.
Yeah, I think, Florian, you have a very good point there. The development time is the bottleneck in many cases, not necessarily the time to completion. And the question is, are quantum computers going to be much easier to program for than normal computers? I'm not so sure.
Okay.
Well, for us, time to completion is a factor. I mean, we're not putting in the effort because we feel it's fun to do that, but so we have dedicated supercomputers in the weather forecasts. So time to completion is like the factor they're looking into. But if that means you have to invest like 200 person years for porting your code, that thing has to provide quite a benefit for people to do it.
Okay, thank you. So we have a new question from Nuno Pereira. He says, let me create some debate. Thank you, Nuno, because these are my favorite questions. So he's asking, don't you think there is a trend in the civil society in questioning science and doubting in experts? Okay, I'm going to copy here in order you could read it. So what do you think about this provocative question?
I personally think you are kind of, or you're hitting the nail on the head, so to say. We see it in the COVID crisis right now in many countries, that a lot of people in the society just don't believe in the numbers, or they are all saying it's fake news. So this is a problem, in my opinion, in and of itself, that basically the experts and scientists who have proof with numbers and figures and their simulation results that they are correct are criticized and doubted. I think, yeah, you're right. It's definitely, there's definitely a trend in that direction.
Mm-hmm. Okay, it is just due to the fake news. Anyone would like to add something to this?
Yeah, perhaps briefly. I think a bit of skepticism is healthy. Scientists can be wrong, and especially in the COVID crisis, there have been many forecasts that have been completely wrong. So a bit of skepticism is okay. It should be evidence-based. And I think the one thing I miss a bit in the media debate is the look back, right? So, for instance, with the coronavirus crisis, we're now about a year in. There have been a lot of people forecasting all sorts of things, and people saying first wave, second wave. There have been people saying, oh, we've got herd immunity in June 2020. Well, that clearly wasn't the case. And I miss a little bit the perspective of people look back and say, okay, these people were clearly correct. These people were clearly wrong. And it's not necessarily the case that the people were correct the first time around were correct the second time around, but you can learn a little bit from that. And I miss that bit of reflection. It seems like when I make a forecast about next month, then next month it gets thrown in the bin. Everybody forgets about it. And then a month later, I'm asked to make another forecast. And nobody really cares whether my previous forecast was correct or not. And that's not healthy. So a bit of skepticism is good. When the skepticism translates into people's lobbying for non-scientific agendas that have only political purposes and no evidence, that's of course very worrying and very dangerous.
Okay, thank you, Derek. I think that's an interesting point because I think never in the recent history in the news scientists had been so exposed to the general public and to their opinions. Okay, and I'm not sure if that's unfair. If we understand the work of the scientists, and it's complicated. Okay, anyone else would like to add something to this topic? If about this trend on the civil society, skepticism about experts?
Well, I would say that just my 5 cents to this topic. Well, sometimes different groups of scientists produce completely different results, and some people tend to believe one group and some people tend to believe the other. And as Derek has mentioned, it's definitely this differences in results, especially in the social sciences, where everything is a little bit fuzzy. It produces some doubt that the science can give some correct answers, and also it produces some trends that people tend to believe different, tend to take different viewpoints. And as Derek said, it is important in this situation to look back and to see what was which predictions were correct and which were wrong.
Mm-hmm. Okay, there is a final question of Nuno Pereira. Thank you, Nuno, for your collaboration and your questions, and I encourage the rest of the audience to ask. So he says, science is not astrology, so it's normal the forecast to be wrong. So the question is the trend that is building, how to invert it. I think that one of the key messages had been the Derek's reflection about to look back to past predictions and to analyze and to learn a little bit about wrong predictions, but also those who had been successful. Okay. Anyone would like to add something to this?
Well, I think there's 2 points. One is that I feel there is a trend of ignoring reality.
Mm-hmm.
So it's not even about science expert details. I mean, it's people working in a hospital, leaving the hospital and feeling like everybody else thinks there is no coronavirus. And those people just like, we're not discussing about a forecast, we're discussing about things that are happening in a very obvious way. And people are like, yeah, nah. And then for the trend, I think one problem is the way social media works, but also media in general, because things always have to be like, if there's something that's scandalous and new and contrasting, it's always good news. And if it's like, yep, and we confirmed things again and again and again, then that's just no news. And so it doesn't get reported and it doesn't get pushed. And so there's just no news, and yep, the weather forecast was right again. Or there's the 75th paper saying that this is going to happen or this has happened. And that's just ignored in basically any form of communication and reporting. And that, of course, puts a focus on things where things haven't really worked, where a detail was wrong, or so I think that also undermines trust. If you just kept reporting and we've confirmed things again,
Mm-hmm.
then people would probably also put more trust into things.
Okay, thank you, Florian. Really interesting to know the point of view of the scientists about this topic. So, well, let's come back to the main focus of this workshop, which have HPC, HPDA, and artificial intelligence technologies. So I would like to ask you, which of these technologies do you think are the most relevant ones and why? So now I will, if nobody, well, I started this time for Sergiy Gogolenko. Would you like to say something about this topic?
Excuse me, Elena, have you?
Yes,
could you please repeat the question?
Of course. The question is, which of these technologies, but HPC, HPDA, artificial intelligence technologies, do you think are the most relevant ones in the current scenario to solve these global challenges, and why?
Well, okay. In my opinion, all of them play a crucial role. Actually, well, we need HPC to run some simulations, and we need HPDA and AI to prepare inputs for the simulations and also to analyze outputs of the simulations. If we take a simulation-centric approach, We can also sometimes tackle tackle some global challenges directly by analyzing of the statistical data. And in this case, we can do it only with HPDA and AI. But in general, if we want to understand the problems, the things that go behind the scene, we want to understand deeper the phenomena which we try to tackle. Then we need simulations, and in this case, yeah, HPC and HPD and AI, all of them are relevant.
Okay, thank you. Anyone else? Christoph, for example.
Yeah, thank you. Coming from a machine learning and AI background, I obviously think that this technology is the most relevant and most important. But all jokes aside, as Sergiy mentioned, all components only work together, and if we are not working together, we cannot gain really good results and tackle those global challenges efficiently. I've seen now in the project with the different use cases where in each use case we at least have 5 to 6 different partners working on it, and everybody plays a vital role in each use case, such that, yeah, just to go along with Sergiy, they only really work together, and only when all technologies are working together, we can really start solving these challenges.
Okay. One step beyond, I would like to ask, for example, now to Fabian, what do you think that it's the future of this type of technologies? How do you foresee the future of these technologies? Or the trends of it? Maybe we are just at the beginning. Do you think that in 5 years we will have a lot of applications for this type of technologies, or it's going to be too much early? How realistic is this scenario, since your point of view?
Ooh, that's hard to say. But of course,
well,
I'm hoping that it's especially these recent developments. If it's like also the research and focus on the applications, focusing, for example, on climate change, on pandemics. Well, this will kind of speed up development, in my opinion. But I'm not the expert for either high performance computing nor HPDA or AI. So I'm more focusing on the applications and kind of the building link. So for me, it's hard to say technically wise.
Okay, thank you, Fabian. And you, Derek, would you be able to
crystal ball moment?
Yes.
I think 2020 is a very interesting one. I think for many years, a lot of modelers have struggled to justify how many jobs do you save, how many lives do you save, etc., etc. I think with the pandemic modeling, it was quite obvious how many lives would saved. You could recalculate that with every wrong or correct or vaguely correct or pessimistic or optimistic forecast. I think people realize by now that simulations make a difference, and that's also why people have such strong opinions about them. As for going forward, I think there's going to be a lot more investment in technology because there's more competition between, say, the EU, China, and the US. So I think there will be more investment in technology. So probably the progress we'll have with, for example, simulations, HPDA, AI, HPC will accelerate a little bit as well. But I think it will move a little bit from just more transistors to trying to make better use of them and have algorithms that can combine the different components more effectively and more easily. So I think we're probably going to see a lot of simulations that are being fed by AI programs that are being optimized perhaps by AI programs, but that then as an output go into a huge HPDA exercise to extract the knowledge that is actual relevant amongst sort of the forest of output data. So I think blending these things quickly, efficiently, and in a way that actually matters for problems that that people care about. That's the big challenge. But I think, yeah, all the solutions will gradually move towards that.
Okay, thank you, Derek. Very interesting. Okay, so I'm going to check if there is any question of the public. No, they are very silent. Okay, so I keep asking questions. So it's a question related to the previous ones. Okay, so now I would like to ask, who do you think is the most relevant interest groups on these topics? Who are the most or maybe even the most relevant interest group, or even I would ask who would be the main beneficiaries of the development of these technologies? So I'm going to ask to Florian, who is looking at me. Okay. I will answer.
Well, I think in the end, we're all trying to serve humanity in some or the other way with these issues, especially when you look at the Sustainable Development Goals. There's this point of like whether you have politics or the public as a target group. And I mean, I think we see it in climate as well as in Corona, actually, that politics has a difficulty with taking decisions that are totally objected by the public. So you kind of need a public support for a policy to actually see it happen. So in some way, if we only cater to politics, but we don't cater to the public will just say no to whatever politicians decide, and that doesn't work. And if we only cater to the public, the politicians will have a tendency of ignoring things. So I think you have to really target both groups in different ways, but you really have to reach out to the public as well. And at least in Germany with climate, the Friday for Future movement has just so much changed the whole debate in the last 2 years. And so it was really the public changing the way politics acted. And then we have a EU New Green Deal and things happening. But you really needed that bottom-up pressure. So and I think for Corona, I mean, you can make rules, but if people are like, oh, I can meet one person at a time, so I'll just meet everybody for 10 minutes today. Great, thanks. So you need this buy-in, and for that you really need to find ways to reach the people.
Okay, thank you, Florian. So there are mainly two interested groups, politicians, which could have better tools to make decisions, but also the general public could have access to an independent opinion of for example, governments. And I think it could be a new power, this knowledge power for the people, power for the people. Okay. So, thank you. I think thank you. Nuno has sent a new question. So, thank you, Nuno. The bottom line, a problem of education, he says. How do you see the next step of education in order to create a more aware public on scientific results and not just politics? Okay, so I'm going to paste this. Anyone would like to answer?
That's well, I've got 2 young children. I think one of them is in the house by now, and the other one I have to pick up in 10 minutes. So as a parent, a problem of education. I think that's a really hard one. But I think it also has to do a little bit with how we educate people. So as a parent, I'm perhaps speaking more as a parent, but I always very strongly feel that I really try to avoid to be cynical, sarcastic, or tendentious with my own children, because I think a lot of people are sort of using emotional momentum either to make their educational job easier because they don't have to answer difficult questions, or they give shorthand answers, shut down conversations, things like that. I think it's very important from a teaching perspective that if a child asks a difficult question that you cannot answer, that you're honest about and say, okay, this is really complicated, I have to look it up. I don't really know the answer. But I think being very truthful, very transparent and direct, and always sort of taking the question in, no matter how weird or ridiculous it sounds, is very important. In terms of the curriculum, I think that sort of open culture can help people also sort of independently analyze and process information in a good way, and perhaps make them less prone to bias. But it's a really difficult question.
Yes.
But I think imposing some very rigid educational program is not necessarily the solution, although there are some fundamental things that everybody should learn about, including Newton's law and I think also climate change. So, yeah.
Okay, thank you, Derek. So, well, our time is running out. So, thank you, all of you. Thank you to the speakers for this conversation and for the presentations. I think that all of us have, after the workshop held today, a clearer vision about how these technologies can help to tackle global challenges. And I would like to say that we will send a link that leads to the attendance to a very short survey. So please, we would appreciate if you could complete this survey, and we'd like to receive your feedback and hear if you have liked the workshop. I hope so. Okay. So thank you for joining to this workshop, and thanks for attending. We will see you next year in the HiPEAC 2022. Thank you.
Yeah, thank you, Elena.
Thank you.
Yeah, thank you all. We're wishing you a pleasant evening. Yeah.